Well, in this video we're looking at frequency modulation. Frequency modulation was introduced in the 1940s as a higher quality form of radio broadcasting than amplitude modulation. This photo is from a demonstration which was held in New York, where an electric arc, seen at the top of the photo here, generated interference whilst there was both an AM and an FM radio receiving at the same time. The AM radio produced only static, whereas the FM radio output was largely unaffected by this massive interference. How does FM work? The instantaneous frequency of the carrier signal is varied in accordance with the amplitude of the message signal. So in this diagram you can see the carrier at the top, and then we see the message signal here. Happens to be sinusoidal here, but it doesn't have to be. And here you can see the frequency of the carrier increases when the amplitude here is the highest, and where the amplitude is the lowest, the frequency decreases. So we have this change in tone or frequency, if you like, in a linear fashion according to the or varied linearly in accordance with the amplitude of the message signal. Now you'll notice that this is very different to amplitude modulation that we saw in the last video. In this case, the amplitude of the modulated signal is constant. It's the same as the carrier signal here. So we're not changing the amplitude, we're only changing the frequency. That's why it's called frequency modulation. How do we generate FM? We put our message signal into this block diagram here, and we add some DC to it. Then we feed that into a voltage controlled oscillator. So an oscillator is just something that produces a sine wave output. The frequency of that oscillation is determined by the voltage going in. So as we vary this in accordance with the message signal, we produce an FM modulated signal out here. That is then fed into a power amplifier which goes to an antenna. So again, here you can see a signal. It's not exactly sinusoidal, but this time you can see, as you saw in the last slide, the instantaneous frequency varies in accordance with the amplitude of the message signal. Now we actually have two different types of FM. We have narrowband and wideband FM. And we have this thing called the modulation index, which is just the ratio of the frequency deviation. How much does the frequency vary plus or minus around the center carrier frequency? And if we divide that by the modulating frequency, we get this value beta, which is the modulation index. Now if beta is significantly less than 1, we get what's called narrowband FM. Otherwise we get wideband FM. Now mostly we generally tend to have beta greater than 1. So we do use most of the time wideband FM. For narrowband FM, if we do happen to use that, the bandwidth is the same as large carrier AM or double sideband suppressed carrier, which we saw in the last video, and that was just equal to 2W. But for wideband FM, the bandwidth is approximately equal to 2W times beta plus 1. So you can see that if beta is larger than 1, we end up with quite larger bandwidth than we do with AM. Regular FM radio in Australia uses a bandwidth of 150 kilohertz with a message bandwidth of about 20 kilohertz. So this makes the value of beta around 75 divided by 20, or about 3.75. Now when you have beta significantly larger than 1, as we do in this case, we end up with the spectrum in the frequency domain. The spectrum of the frequency modulated signal is significantly wider, and we have multiple sidebands. So remember, from double sideband suppressed carrier, when we just had a sinusoidal modulating signal, we had the carrier plus an upper and a lower sideband. Well, now with frequency modulation we have multiple sidebands at integer multiples of the modulating frequency. So this is FC, FC plus FM, FC plus 2FM, 3FM, 4FM, 5FM, and so on. So you can see this signal here, it has quite a large value of beta. So here you can see if we have a small value of beta equals to 2, or relatively small, versus beta equal to 4, you can see the significantly wider bandwidth. And as we increase beta, we get a much larger bandwidth. The amplitudes of each of these sidebands is given by a very complex set of mathematical functions called Bessel functions of the first kind. And you can see the plot here of these Bessel functions. And when we have a small value of beta, we can see that most of the energy is contained in the first couple of sidebands. But as we increase the value of beta, here you can see the largest one for beta equal to 12, we have sidebands going all the way up to 14, 15, 16. So that will generate a very wide FM signal in terms of bandwidth. Okay, so depending on the value of beta will dictate the bandwidth or the spectrum of how much we use. Now when we want to demodulate FM, we can either do that non-coherently using a slope circuit, or otherwise known as a simple filter, and all that does is convert frequency changes back to amplitude changes. Or more typically we would use a coherent method. In this case we're using a phase locked loop, and this is just a first order phase locked loop. There are many different types of PLLs that one can use, but this is a very simple one, and this results in better performance than the non-coherent method. So we can appreciate that there's quite a big difference between AM and FM. FM uses much more spectrum or bandwidth in order to achieve that better noise performance. Now in radio broadcasting in Australia, you can see here that we have spectrum in the range of 540 to 1600 kilohertz with 106 possible frequency bands, and they are 10 kilohertz wide. FM, on the other hand, uses bandwidths of 150 kilohertz, so 15 times more bandwidth. Now why do we do that? Well, audio signals that the human ear can hear typically are in the range of about 20 kilohertz or less. So AM doesn't use the full bandwidth, whereas FM does. It uses the 20 kilohertz bandwidth, so it's going to sound a bit better even just because of that. But it also sounds better because we're using frequency modulation and we get a better noise performance. So the signal which is transmitted through the air is not disturbed by interference from other sources of radio transmission. So FM uses 200 kilohertz bandwidth spacing, 88.1 to 108.1 megahertz. So there's about 100 possible bands. So we can see that frequency modulation then trades off the use of more spectrum, more bandwidth for better noise performance. And that's a classic case of a trade-off in telecommunications. Any telecommunications systems always ends up with a trade-off between two fundamental properties, and those are power and bandwidth. We can never build a system that has an improvement in both power and bandwidth at the same time. There will always be trading off one against the other. So that brings us to the end of the section on continuous wave modulation. So we've talked about AM and FM. We haven't talked about PM, but PM is really just a kind of special case of FM. They're very closely related. So pretty much exactly the same thing. So in the next video we're going to talk a little bit about pulse analog modulation before we then move on to digital modulation.